Properties of waves. Vocabulary: amplitude, wavelength, frequency, and period. Today we're going to talk about the properties of a wave. Recall the two types of mechanical waves we learned about in the last video: transverse and longitudinal. Transverse waves had the energy moving in one direction and the wave traveling at 90-degree angles to that energy motion. Longitudinal waves had the energy moving in the same direction, but the wave would move in the same direction as the energy. We're within the same plane. That's my attempt at a slinky, in case you're wondering. But looking at these, how do we tell the difference between two transverse waves and two longitudinal waves? To better understand this, let's look at a couple of transverse waves. So here we have two transverse waves. The first thing you probably noticed about these two waves is the differences in size from top to bottom that they travel. So if this is the middle of the wave, and this is the middle of the wave, the yellow wave travels a lot farther up and down than the red one does. This change in height is called amplitude. So our amplitude is the distance from the middle to the top or bottom of a wave. And it's labeled with a capital A. So amplitude is a capital A. The top of the wave is called a crest, while the bottom is called a trough. So here we have a crest and a trough. Looking at these two waves, we can actually measure the amplitude of them. So my other two waves, we didn't know how far they traveled, but using these two, we can actually measure how far the wave travels. So our red wave travels up 0.5 meters and then travels down 0.5 meters. So our amplitude, so A for the red wave, equals 0.5 meters. For our blue wave, we only go up 0.25 meters and then down 0.25 meters. So A for the blue wave is 0.25 meters. But what does this tell you about waves? You don't care if one's bigger than another, do you? Amplitude actually is a measure of the energy contained in a wave. The larger the amplitude, the more energy it carries. So our red wave carries more energy than the blue one does. Another thing you probably noticed is that there's the distance between red waves is shorter than that for blue waves. So the distance between 2 points on a wave is called the wavelength. So wavelength, distance, between identical points on a wave. So we have two crests, so two identical points on a wave. But we don't really know where those crests are at as far as distance goes. So what we can do is we can backtrack down until we hit the x-axis. So we still have two identical points. The graph is going up to the right in both situations, and it's on the x-axis, so it's easier to measure. So for this red wave, we have our farthest point is at 4, so 4 meters, and our closest point is at 2 meters, so our wavelength is 2 meters. And the symbol for wavelength is the Greek letter lambda. So wavelength is symbolized by lambda, and we said for our red one it was 2.0 meters. Now for the blue wave, we have to work a little harder to get our wavelength. For the blue wave, we start out here. We only have 2 crests to work with, so we'll start with those. We have to backtrack again. So we have to backtrack down to 0 and backtrack back down here. So our farthest point is at 4. So our wavelength equals 4. And our close point is 0. So 4 minus 0 equals 4.0 meters. So that's the wavelength for our blue wave. Another thing that you probably noticed, or let's say that instead of meters on the bottom, if we said this was a snapshot of 1 second, so this is a picture of our wave for 1 second. This means that our red wave travels, so the red wave travels 6 meters in 1 second, and our blue wave, or our red wave repeated, so we went here, so that's 1, that's 2, that's 3. So we had 3 waves in 1 second, and our blue wave went, there's 1 wave, and that's a half wave. So we had 1.5 waves in 1 second. This tells us our frequency. So frequency, which is given by a symbol F, is the number of waves that pass a point in a given amount of time, or typically 1 second. So the number of waves that pass a point in 1 second. So like we said, our red wave has a frequency of 3, and our blue wave has a frequency of 1.5. And for frequency, instead of saying waves per second, we can just say hertz. So our red wave has a frequency of 3 hertz, and our blue wave has a frequency of 1.5 hertz. So that tells us how much the amplitude of a wave, tells us the distance between waves, or the wavelength, and it tells us how many waves pass a point in a given amount of time. So the only thing left to calculate is the amount of time that it takes one wave to travel past, or how long it takes one wave to travel past the point. So in order to do this, let's go back to frequency. So our frequency of the red wave was 3 hertz, or 3 waves per second. And what we're trying to calculate is how many seconds per wave, which is known as the period. So this is our period, which is denoted by a capital T. So to go from frequency to period, all you really have to do is divide 1. So period is equal to 1 over your frequency, which flips your symbol. So instead of waves per second, it becomes seconds per wave. So for our red wave, we had frequency is 3. So for a period is 1 divided by 3, which equals 0.33, and this is in seconds because the period is number of seconds per wave. So 0.33 seconds is our period. For the blue wave, we said we went 1.5, so frequency equals 1.5 hertz. And so the period for the blue wave would be 1 divided by 1.5, which equates to 0.67 seconds per wave. Let's look at one more example quick. So if I told you I'm going to give you a wave. This wave has a frequency of 4 hertz. I just made that up and gave it to you. So frequency is 4 hertz. If I asked you to find the period of that wave, what would you do? You would know that the period is equal to 1 divided by the frequency. So in this case, it's equal to 1 divided by 4, which gives us 0.25 seconds. Likewise, if I told you we had a period, we knew that the period of a wave was 10 seconds. We could find the frequency because the frequency is equal to 1 over the period, just like the period is equal to 1 over the frequency. So in this case, our frequency would be equal to 1 divided by 10, which gives us 0.10 hertz. This has been Ben Gehring talking about the properties of waves. Have a fantastic day.